All right. Next lab on the agenda. Determining density. It's a very simple lab. I like simple labs. And these are the materials that we're going to need. Won't take much. We're going to determine the density of a liquid and two solids. The liquid is going to be 2-propanol, which is isopropanol, rubbing alcohol. Only this propanol is not the same as the rubbing alcohol you get in the stores, which is about 70%. This is 100% pure 2-propanol. Okay, so density. What is density? Density is an intensive factor. That's what the authors call it. It's an intensive property, which means that the value of density does not change for any amount that you have of the substance. So we can measure the density of 2-propanol using 10 milliliters or 1,000 milliliters. It doesn't matter. The density is the same. That's an intensive property. An extensive property does depend on the amount of matter you have, like the mass of something or the volume of something. Now, I like to call the extensive property a capacity factor. It's easier for me to grasp that terminology. And the other, the intensive property, is the capacity factor versus the intensity factor. Okay, so density. Density is equal to the mass of a substance divided by the volume of that mass. So you just divide M, say if you can see this, D equals M divided by V. It's a formula. All right, so here's what we're going to do. First, we're going to find the density of the liquid. Safety factors. Let's go back to the back page, pre-laboratory assignment. All right. So what safety precautions should you take when working with rubbing alcohol, 2-propanol? Well, you don't want to get any of it in your eyes. Of course, you want to cover your eyes, splash protection. This pure stuff might be irritating to some people, so you want to wear gloves, and I'll put my gloves on in a second. What else? Any type of organic compound, like an alcohol, is flammable, especially if it's 100%. So you don't want this near any open flames. Okay? Define the terms. Density, I just did. You can do that here. Extensive property, I defined that also. Okay, number 3, a student determined the density of an unidentified liquid known to be one of the following 4 compounds. He found that 7.3 milliliters of the unknown had a mass of 6.52 grams. What's the density of the unknown liquid? Simple. Density is a formula. Mass divided by volume. Mass divided by volume. That's it. The density of the unknown liquid is easy to calculate. Identify the unknown. Once you get the density, then look at the list. So we have acetone, ethyl bromide, ethyl chloride, ethyl iodide. Pick from that list based on the density. And then identify the unknown. What's the mass of 9.5 milliliters of ethyl iodide? So we have a formula. Density equals mass divided by volume. Let's go to the board. Okay, see if you can see this. Density equals mass divided by volume. if we're saying ethyl iodide, look at your list. Ethyl iodide has a density of 1.94 grams per milliliter. 1.94 grams per milliliter. And you're also given a volume of 9.5 milliliters. What do we have here? We've got the volume, we've got the density, the unknown is mass. Any formula that has one unknown is solvable. You just use your algebra. What is M? Take this one over here, multiply it times that one. That's your mass. Why? Because when this is multiplied by that, milliliters cancel, leaves you with grams. So I'll let you do that. Crunch the numbers yourself. What is the volume of an acetone sample whose mass is 6.95 grams? Acetone, you need the density, which is 0.79 grams per mil. So it would go in here. And you have a mass of 6.95 grams. So how would you solve for the volume in that case? Well, the volume would come over here, density would go over there, divide the density into the mass, you get the volume. A collection of glass beads has a mass of 29.33 grams. The beads were transferred to a graduated cylinder containing 13.5 milliliters of water. The volume of the water plus the beads was 25.2 milliliters. Calculate the density. All right, we're going to do something like this in just a minute. So if you have a graduated cylinder, right, and it contains 13.5 milliliters. Okay? Then you put the glass beads in it. So what's going to happen to the volume of water? It's going to go up because you put volume in here to displace the water. It's going to go up to 25.2. All right? Now, you've got the mass of the beads at 29.33 grams, right? We're asked to calculate the density. So there's your mass. What's the volume? The volume is the difference before and after you put the beads in it. So 25.2 minus 13.5 is the volume. Calculate the density. All right. So that was the pre-lab questions. Now we can get to the lab itself. And we need directions. Here we go. And of course, you should have read this before you start the video. Right? Anybody that walks into a lab and does not first know what they are going to do in the lab before they walk through the door is not only unsafe, but they're a fool. All right, obtain 10 milliliters of rubbing alcohol in a 50 milliliter beaker. All right, so this is an estimated amount. So we have a 50 milliliter beaker, and I'm going to need my gloves. Let's be safe. Gloves and gloves. I will dispense a small amount in here. And there we go. Now, how are we going to determine the density of that liquid? What do we need to know to do the density? Look at the formula. We need a mass and a volume. So how do we get the volume? The volume is just measured directly from the container. How do we get the mass of a liquid, though? You can't carry the liquid over there in your hand and slop it on the balance and get a mass. It has to be in a container because it's a liquid. So we do it by difference. If we know the mass of the container first, then we add liquid to it, take the measurement of the mass again, then what's the difference in the mass? The difference in the two masses is the mass of the liquid. So first, we need the mass of the dry container, of the 10 milliliter. Let's see. I better bring this with me. So here's our analytical balance. It appears to be zeroed. Let's tear it again. Okay. Now we need the mass of the container. I'm not going to be able to shut the lid, so we'll just have to be satisfied with what we get. 27.938. 27.938 is the mass of the 10 milliliter graduated cylinder. Oh, by the way, when we're filling out this form, the identification code of the rubbing alcohol is just 2-propanol. What's the mass of the graduated cylinder? Well, it's changed a little bit. Let's say 27.941. 27.941. And grams are right here, so we don't have to put grams out there. Now, we're going to add some rubbing alcohol to the graduated cylinder and measure the mass again. So how much do we add? The method calls for 5 or 6 milliliters, right? So that just means we add up to near 5 or 6 milliliters, and then we actually read the exact volume from our cylinder. So let's see if I can do this steady-handed. 5 or 6. Let's shoot for 5. Coming up. 2, 3, 4, and in the neighborhood of 5. Now let's see exactly how much we put in there. All right, I need something white behind it. It's difficult to see. There we go. So now at eye level, I can read 5, and let's see, 5 to 6. Each one of these marks is 0.2. So I've got 5, looks like 0.25, because my last one, no, I can't do that measurement. I've got to estimate between 0.2 and 0.4. So 5.3 milliliters. So the volume that's in the container is 5.3 milliliters. Now let's determine the mass of the container plus 5.3 milliliters. We're zeroed. And I keep forgetting my paper. $31.93 31.939. 31.939 grams. Okay. Now what are we going to do? Well, the method says add some more. So now we're going to get a new volume and a new mass. So how much more does it want us to add? That's the $64,000 question. 2 to 3 milliliters more. All right. So let's say 3. We'll go up close to 8. Let's go past 8. Just guess right there. Okay. Now, at eye level, got to get eye level. One thing about these graduated cylinders is you'll notice that they're every so often you have a line that goes all the way around to the back. That's so if your eye is not level with the line in front, you'll see 2 lines. If your eye is level with the front one, 2 lines will disappear. So that helps you keep your eyes level. So let's move up. All right, we're level with this one. We need just to be a little bit higher, kind of in between this one, about right there. Okay, so I've got 8.4 milliliters. 8.4 is the new volume. Now what's the new mass? $34.357. 34.357 milliliters. There you have it. We have all the data we need now to calculate the density of isopropanol in replicate. Replicate means 2 or more determinations. So we have actually duplicates. We have measured 1, then we measured 2. Okay, that will be used in calculations later in the experiment. Now we're going to move to the density of a rubber stopper. All right, we don't need to keep the rest of this, so I'm going to pour back in here the isopropanol, set this aside, and it will evaporate small amounts. Now this, I'll take that and dispose of it properly. But you never put anything that you draw out of a reagent bottle, you never put it back in the reagent bottle. For one thing, it could contaminate your reagent. For the other thing, you may not know what exactly is in that material that you took out. You might put something back in there that's incompatible with it, and you have a reaction. So never put anything back in the bottle once you take it out. All right, so we're done with the isopropanol. Set it aside over here, deal with it for disposal later. Now, for the rubber stopper here, what do they want us to do? Identification code for the rubber stopper. I'm going to say the identification code for this rubber stopper is actually its number. All rubber stoppers have numbers, and the bigger the number, the larger the stopper. This is a number 3 rubber stopper. So I'm going to put a number 3 right there. We need mass and volume. So the mass is easy. We just bring our paper with us. Be sure we're set on 0. It doesn't want to settle down, does it? Give it a chance. There we go. Put the stopper on there, close the lid. Now we're going to get a stable number eventually. 11.016. 11.016 grams. Now we need the volume of the stopper. How do you get the volume of an object? Well, there are 2 ways. If it's a regular object, you can measure its dimensions. So if this were a cube, all we need is to measure the sides, or a rectangle, the sides. Or a cylinder, we'd measure the diameter and the length and use a formula to get the volume. But this is a rotated trapezoid. Notice this side's shorter than that side, These two lengths are the same. So we could theoretically calculate that by just measuring the dimensions, but there's an easier way. Do it the way we did the glass beads, by difference of volume, and all we need is a liquid that will not absorb into the rubber stopper. Water's a good one. So what we'll do is add about 50 milliliters of water, okay? It doesn't have to be exact until we determine the actual volume. Okay, that's good. Now, what's the starting volume for that cylinder? That's the volume of the water on your data sheet. So the volume of the water at eye level is, let's see, it's kind of hard to see those lines, isn't it? Black is better. Let's use black background. Okay, eye level. That's about, let's see, no, exactly. 50, 1, 2, actually 52.0. 52.0 milliliters is the volume of water. 52.0 milliliters. Okay. Now we add the stopper to it. And the difference in volume before and after is the volume of the stopper. So we want to do it without splashing. All right, so we'll slide it in there and gradually lower it into the water. There we go. There you have it. Now let's measure the volume of water plus stopper. And as you may have guessed, the volume is higher. Okay, let's see. Eye level. So I've got 60, but not quite 61. 60 point, looks like about 7. 60.7 milliliters. All right, so just estimating, I would say 8.7 milliliters of volume, and the mass, so the mass divided by the volume will give you the density. And we'll do those calculations on a different page. Okay, one last one. First we have to do is, for the water, this is distilled water, no potential for hazard of contamination, and then get our stopper out. You can dry it with a paper towel, but I'm going to set it aside and let it evaporate. Okay, what do we do for what the method calls for an unknown object? I'm just going to tell you what the object is. So the identification code of the object is ZN for zinc. And we have cylinders of zinc right here. Here's one of them. Here's a cylinder of zinc. Okay? Now, this is a regular object. We could measure the dimensions and calculate the volume. But we're going to use the simpler method. We're going to start with volume and then add the zinc and see what the volume is by difference. So we'll get up here like that. And before we do that, of course, what do we need? We need the mass. So let's go over here. It's still dry. 0. And the mass of our zinc is 28.563. 28.563. By the way, what do we know qualitatively about the densities of that stopper and probably the zinc. We know that if an object is less dense than the liquid in which it is submerged, it will float. So since the rubber stopper sank and this zinc pellet is probably going to sink, that their density should be greater than 1, greater than water. If you try to do this by difference with something that's less dense than water, then simply putting it in the water is not going to work, because only part of it will be submerged. And that's the part that displaces the water. So you have to modify your procedure, and we don't have to kind of go into it right now, but we need a beginning volume. So the volume before we put the zinc in is, let's move that out of the way so I can see black background. My goodness, that's sitting right on 50. 50.0 milliliters before. Now we're going to add the zinc in such a way that we don't crack the bottom or splash the water. So we put it in here on edge and sink it like that. Okay. Now, I see a bubble on my zinc. Dislodge the bubble. There we go. Now, let's check our volume at eye level. 51, 2, 3. Sitting right on 4. 54.0. 54.0 milliliters. Okay, that's all the data we need. The rest is calculations and answering questions. So let's retrieve our zinc. Now the method calls for the instructor to give you a list of densities for the objects. And then you determine the density and pick out what material best corresponds to that density. But in this case, I'm telling you it's zinc. So all you have to do is report the density of the zinc. Pour the water out. Here we go. And set it aside to dry. There we go. Now, let's see if I can help you a little bit. I'm not going to answer all the questions for you. Calculate the mass of each sample using the mass of the cylinder plus determining the density of rubbing alcohol. So what's the mass of sample 1? That's easy. You just transfer it from this one to that page. No, you do it by difference. Excuse me. Do it by difference. So the mass is going to be this value for 1 minus the value of the container. And for 2 is going to be this value minus the value of the container. Right? So I just told you how to do it. I don't need to write it in there. Next, calculate the density of each sample of alcohol. For that, you just say you got the mass, you got the volumes for each one. So the mass of 1 divided by the volume of 1. And it's not this number, it's the number you calculated here as the difference between the total mass and the mass of the container. Okay? Do the same thing for this one. You determine the mass of the sample by subtracting the container from the new mass of the second weighing. Divide it by the volume that you determined for the second weighing, 8.4 milliliters, and you have your density. Now, what does this one not have? This one does not tell you what the units are. The units are going to be grams because we measured in grams. How about the units here? Grams per milliliter. Don't forget the units. If the units are not already written for you, You better put the units there, or your answer's half wrong. So how do you determine the average density of the rubbing alcohol? The average is just add them all together and divide by the number of things you have, right? So you add those two densities together and divide by 2, and there you go. Identification code for the rubbing alcohol is just 2-propanol. Okay, you can do that. Now, what's the volume of the rubber stopper? The volume of the rubber stopper is the volume of the water subtracted from the volume after you add the stopper. All right, so we have 8.7. So you put that there. And you put the units, milliliters. All right. Now, the density of the rubber stopper is you divide that number of milliliters into the mass of the stopper. And the identification code of the stopper is a number 3. There you go. Last one, unknown object. The unknown object is zinc. So down here at the bottom, composition of unknown object zinc, identification code zinc, ZN. And you will have memorized those. Zinc is one of those elements that I told you to memorize. So you should know that one by now. So, what's the volume of the unknown object, which is zinc? The unknown object volume is before subtracted from after. It looks like 4 milliliters. So you write it in there. The volume of the unknown object is so many milliliters. What's the density? You take the mass of the object and divide it by the determined volume that you just put in that on that line. There you go. And it's grams per milliliter. Now, by convention, solid objects are reported as grams per cubic centimeter, and liquids are reported as grams per milliliter. You know what the difference is? There's no difference. The same number has different units because 1 milliliter is equal to 1 cubic centimeter. But in this case, it's going to be grams per milliliter because those are the units that we determined by measurement. So just use those values. Don't bother converting. It's just grams per milliliter for the solid object. Okay, we did the pre-lab already. Let's go back to post-lab questions. All right, I'll see if I can give you a little help here without actually feeding you answers. Compare the densities of your 2 rubbing alcohol samples. All right, so we did determine 2 densities for the rubbing alcohol, or the 2-propanol. Were they identical? Yes or no? And if they were not identical, why do you think they were different? Which means, what are the possible errors that could have been made to give you different numbers? You could have made errors in mass, or you could have made errors in volume. That's the only 2, right? Because density is mass divided by volume. Where could you possibly have made an error in mass or in volume? Should these densities have been identical? Now, what's the first lesson you learn about measurement in science? Every measurement has error. So what does that mean about the densities? Should you expect them to be identical values? No. You should be surprised if the values are exactly the same. Let's see, suppose you had been asked to share your rubber stopper with your laboratory partner. To do this, you cut the stopper into 2 pieces and determine the density of your piece. Should you report your experimentally determined density as the density of the stopper, or should you add the density you determined to the one your partner determined and report this as total density? The answer to that question lies in what type of measurement is it? Is it a capacity factor or an extensive factor? In which case, the amount of the material does matter. Or is density an intensive factor or an intensity factor or property? The answer is the latter. And intensive properties do not change with the amount of the material. Right? So if the density that you determined and the density that your partner determined are intensive factors, why in the world would you want to add them together? That would be foolish. So, suppose that when you add your rubber stopper to the graduated cylinder containing water, some of the water splashed out. There's your error. You lost some water. Would your experimentally determined density of the stopper be erroneously high or erroneously low? Answer to that question lies in the formula of density itself. Look, density equals mass divided by volume. So what changed? If you lost volume in the process and V becomes smaller, what happens to D? If the denominator gets smaller, what happens to the quotient? The quotient gets bigger, right? So if you lost some volume, when you divided it into the mass, which was not in error, what happens to the density? Does it get bigger or smaller? I'll let you answer that. Suppose that after a student added his unknown object to the cylinder containing water, the top of the object remained above the surface of the water. That means the object was less dense than water. So if it remained above the surface of the water, how much water are you displacing? You're only displacing part of the volume of the object. After reading the new water level, he calculated the volume of the object. Would this be high or too low? Think about it. If the volume depends upon immersing the entire object, which way would it go? If you don't submerge the entire object, then the volume would have to be lower. Put that in your own words. Were the volume measurements you made using the 10 milliliter graduated cylinder more or less or equally precise as the volume measurements you made using the 100 milliliter graduated cylinder? All right, that's simply looking at the cylinders and seeing what's the finest possible measurement that can be made with either. And you can say, look at the 10 milliliter. What is the smallest what's the smallest mark on this one? The smallest mark is 0.2 milliliters. What's the smallest mark on this one? 1 milliliter. So figure that one out. Which one is more accurate? Number 5, we said that knowing only the density of a substance is not sufficient to identify it. That's true. Yet in this experiment, you identified the composition of a substance by its density. Right? That was in the PreLab question. What other information did you have that allowed you to make the identification? Well, the only thing that allowed you to make that identification was you had a list to choose from. Your instructor said, the object is definitely from this list. Right? Otherwise, you don't know for sure. In order to determine the substance accurately, you would need some other form of identification, right? Some other analytical method to determine the substance, and we don't have that. So you're relying on the instructor to have given you a list of choices that include the unknown. The density of water at 0 degrees centigrade is 0.9999 grams per mil. and the density of ice at 0 degrees is 0.9168 grams per mil. Based upon these densities, does water contract or expand when it freezes? Okay, look at the densities. So if density equals mass divided by volume, and the density when water freezes goes down, does the mass change? No. You can't create or destroy mass, but you can change the volume. So what happens? If it goes from a high density to a low density and the volume changes, in order for the density to decrease, the volume must increase, which means what? Contract or expand. Okay, suppose you have a 250 milliliter container completely filled with ice. What volume of liquid water will form when the ice melts? Okay, for this one, this is a little more difficult. For this one, you only need the ratio of the density of water versus ice. So what volume of liquid will form when the ice melts? If this is the volume of the ice, then is it going to get smaller or larger? It's going to be less than 250 milliliters when it melts, right? Because it's more dense, it has to contract. So what you need is 250 times the ratio of the densities. But if it's going to contract, you need a ratio that will be less than 1. Right? So you need 0.9168 divided by 0.9999. And that will give you a value smaller than 1, and the value will be the new volume. Okay? Now, in part B, would water spill out of the container once the ice melted? Well, no. If the ice melts and becomes smaller in volume, then it would not spill out. How much water would spill out? Well, we just said it wouldn't, so there's no water spilling out. How much water could you add to the container after the ice melted? Aha! So if it contracts and gives you this volume, how much did it contract? 250 minus this amount. That's the answer there. All right. So this lab is done. All you have to do is fill it out, complete it, scan it or photograph it, and turn it in on Blackboard.